In this video, we introduce the definition and notation for logarithmic functions. Because logarithmic functions are the inverses of exponential functions, we begin by reviewing what we already know about exponential functions. For positive a not equal to 1, the exponential function with base a is given by f of x equals a to the x power. Let's review the properties of the graphs of exponential functions. The points 0, 1, 1a, and negative 1, 1 over a are on the graph. If a is greater than 1, then the function is increasing, and if a is a fraction between 0 and 1, then the function is decreasing. In either case, the exponential function is a one-to-one function. The domain is the whole real line, and the range consists of positive real numbers. Finally, the x-axis, or the line y equals 0, is a horizontal asymptote. The critical property for us currently is that all exponential functions are one-to-one functions. This matters because one-to-one functions have inverse functions. Recall that inverse functions undo each other under composition. An alternate but equivalent definition of inverse functions says that two functions f and g are inverse functions provided that y equal f of x if and only if x equal g of y. Note that in this definition we see clearly that f and g interchange the variables x and y. By definition, logarithmic functions are the inverses of exponential functions. For positive a not equal to 1, the logarithmic function with base a is the inverse of the exponential function with base a, and is denoted by y equal log base a of x. Log base a is the name of the function. X is the input or independent variable, and y is the output or dependent variable. If we let f of x equal log base a of x and let g of x equal a to the x, then the inverse property says that y equal f of x if and only if x equal g of y. In particular, y equal log base a of x if and only if x equals a to the y power. This last statement is the one that tells us how logarithmic functions actually work. It turns out that logarithms are exponents. We use the inverse relationship to determine what log base a of x means. Verbally, log base a of x is the exponent to which the base a must be raised to produce x. For example, log base 5 of 25 is the number to which 5 must be raised to produce 25. Therefore, log base 5 of 25 equals 2. Let's practice evaluating some more example logarithms. Log base 2 of 8 equals the number that 2 must be raised to produce 8. So log base 2 of 8 equals 3 because 2 cubed equals 8. Log base 3 of 81 equals 4 because 3 must be raised to the power 4 to produce 81. Similarly, log base 3 of 1/9 equals negative 2 because 3 to the negative 2 power produces 1/9. Log base 25 of 5 equals 1/2 because 25 to the 1/2 power is the square root of 25, which equals 5. Log base 10 of 1/1000th is negative 3, because 10 to the negative 3 is 1/1000th. The previous examples each contain two equations, one in exponential form and one in logarithmic form. Being able to convert from one form to the other will be essential in solving logarithmic equations, the topic of a future video.